Hi, can everyone hear me? Cool. So my name is Arshia, and I like to do a lot of things on the internet, some of which I will talk about today. I like looking at Harry Potter /fiction. I like tweeting. I like looking at Rust documentation. And all of this is possible because of the world's largest and my personal favorite distributed system, which is DNS, which stands for Domain Name System, for those of you who didn't know about it. So this talk is going to be about DNS. Before I talk about the design of DNS and the structure of DNS, I want to talk about Elizabeth Feindler. The domain name system was created by Elizabeth Feindler, who in the 70s and 80s managed something called the Network Information Center. The Network Information Center was basically a reference for the state of the internet as it existed at the time, which was basically a bunch of universities and government projects. But often people wanted to know who was on the internet, what were the addresses of machines on the internet, and that's what the NIC provided. But soon email came along and everyone was getting on the internet and trying to send messages to one another, and the internet was growing. And there was this need to sort of let people know that if they wanted to address a certain domain, how to get the address of that domain. Before, the way it worked was people actually published handbooks and mailed them out to people who needed that information. But as email came along and the internet grew, Elizabeth was like, hey, let's automate this because we're all engineers here. So this is the automation that they did. There was a file called hosts.txt that was literally copied over the network onto every machine that was on the internet. And it basically contained a list of every domain, like CMU11, ETAC, FNWC, and mapped it to an address. And this eventually grew and scaled up and became better and more fault-tolerant and more resilient to become the domain name system that we know and use today. So this is how DNS works. My laptop is like, hey, DNS, I need the address of tumblr.com. And DNS is like, here is a long 32-bit number, possibly even a bigger, not a 32-bit number if we move over to IPv6 quickly enough. But this is the address of tumblr.com, and the slashfic loading begins. Side note, the addresses here are really weird, right? They're not like IP addresses. This is because this was pre-TCP IP. They used a protocol called NCP. I don't know what NNC stands for, but the P stands for protocol. And the address space of this protocol was only 256 because I guess they didn't think they needed addresses that were more than that. But yeah. So a couple things about DNS. The first is that it's relatively fast, right? If my laptop needs to first look up the address of something and then go to the address, you want that first step to be as fast as possible. The second is that it's pretty reliable, right? If you can't connect to a web server or load a website, it's rarely because there's a DNS error and more because the web server itself has a problem. And the third is that it's pretty correct. So if my laptop wants the address of tumblr.com, it's probably going to get the address of tumblr.com and not twitter.com or facebook.com. And this is pretty interesting because shit is messed up behind the scenes. Machine breaks, data is missing or far away or not available, connections drop all the time, data is sometimes wrong. And so basically what I'm trying to say is that distributed systems like DNS are lying to us all the time because they're quietly breaking and failing and crying, but at the same time, this is possible. So DNS seems to work and not work at the same time, and this is what my talk is going to be about. So say I go to Waterloo, still a student, so say I want to go to cs.uwaterloo.ca to look up something, because I want to. The way DNS works is that addresses are stored in a sort of hierarchy. So at the top we have something called root servers, which store the address of all the TLDs, so .ca, .com, .gov, .eu, etc. A level below that, there's TLD servers, which store the address of all the domains that end with that TLD, and so on. And these root name servers at the top are really important because conceptually they're the beginning of every DNS query. And there used to be 13 of them in the world, labeled A to M because programmers, and 10 of the 13 of them were in the US because politics. And this was kind of good at the time because if you had 13 machines and a couple of them went down, that was kind of okay, right? Because you could still reach some of them. But this isn't good enough now because having the weight of the whole internet rest on 13 servers is just bad. So in reality, DNS servers use a concept called anycast, which means that instead of one IP address mapping to one machine, they map to multiple machines. And this feature of DNS is super essential because it adds redundancy to DNS. And this gives us a couple of advantages. The first is that it makes DNS resilient. Even if like tens or hundreds of the thousands of servers that are up go down, that's still fine because traffic can still go up, DNS queries can still be resolved, people can still use Twitter, which is what matters here. And the second is that it makes DNS fast, because having hundreds or thousands of machines instead of 13 means that the average request has to travel less far to resolve a query. Now, speed is really, really important to DNS, and Anycast does provide that, but using Anycast still means that you have to talk over the network. So there's one major strategy that we use to add speed to a system: caches. Love caches. So as we saw before, DNS queries start with like the root name server, and they go on to the TLD name server, and then they go all the way down. But each result that the DNS server gets is actually cached at every level. So the root name servers, their addresses don't change very often, so they're stored for a very long time. Com TLD servers, their names change, like their addresses change every so often, so they're stored for a long time. Twitter.com might change more frequently, so the address isn't stored very often. So here's a fun little example. I used a tool called dig to resolve cats.com, and this is the IP address of the local name server that I was connected to, and the 3600 up there in the DNS record means that that name server had cached the record for cats.com for 3600 seconds or 1 hour. Now, speed is a really fundamental part of DNS. You might think that DNS would just be like slow if we took caching out, but it would legit break if like every like cell phone and server and like internet connected toaster issued queries to the root name servers to resolve DNS queries. Caches are really, really integral to DNS being what it is. If caches didn't exist, there'd just be too much traffic. So servers would get overwhelmed and queries would time out. Second, applications would be way slower than they are right now if the network first had to if applications first had to talk over the network to get the address of a server and then like use the address of the server to like actually load what they want to. Now, all of this work is being done by the resolver of whatever network you're connected to. Why is there a coffee? Oh, right, yeah, I'm in a cafe. That's why I'm drinking coffee. So the point I want to make is that as we resolve DNS queries, what our laptop is doing, what our computers are doing, is trusting the resolver of whatever network we're connected to tell us the truth. So I trust that when I ask my Chrome browser or whatever to load cats.com or tumblr.com for me, that's exactly what I'm going to get. So besides caches and besides redundancy provided by Anycast, the third like unspoken component of what is really making DNS work in this scenario is trust. Unfortunately, trust is really not something we can afford to give out because like servers lie all the time. And lying DNS servers can intercept requests and intercept responses, steal information, spread viruses, and so on, especially if you're on an unencrypted connection, which DNS by design allows. And people have taken advantage of this in the past. So in March of 2014, people were not tweeting great things about the Turkish government. And so the government of Turkey got mad and they just blocked Twitter in all of the country. And they did this at the DNS level. They did this by like configuring the ISPs in Turkey to direct twitter.com to like a Turkish website instead of actually Twitter. And in this case, people were able to get around it because they directed their machines to Google's public DNS server, which like they spray painted all over the city, which I thought was pretty great. So to end this talk, I want to talk about some thoughts I have about like the design of DNS. When DNS came around, it's because everyone was getting on this hot new fangled technology called email, and they wanted to use the internet. So the concern that the Network Information Center and that Elizabeth Feindler had was scale, not security. But trust without security has not worked out so well for us because people, malicious actors, have used it to create DDoS attacks and man-in-the-middle attacks and poison DNS caches, and this has led to like serious incidents in the past. And I'm really interested in solutions that people are creating and proposing to sort of directly tackle this. So a really simple solution, or a very common effective solution, is TLS. TLS is used whenever you use HTTPS instead of HTTP to sort of browse the internet on your browser. And this does two things. It encrypts messages between servers, so even if information is stolen, it can be decrypted. And B, it requires servers to prove who they are using math and cryptography and fancy stuff. But the point is, you will have a guarantee of like who you're talking to. And the second is this really interesting thing that I learned about and read a lot about on the Cloudflare blog called DNSSEC, I think. And DNSSEC is a set of security extensions to DNS. So it sits on top of DNS, and it proposes all these cryptographic signatures that take place at each process of the DNS lookup to sort of authenticate every DNS record that is being sent back and forth as queries get resolved. And it was introduced in 2005, and it has, the people who've been trying to get everyone to adopt it have been sort of dealing with a lot of back pressure because you need to provide backward compatibility, and it's extremely hard to deploy given how widespread and big DNS is and the scale at which they're operating. But I'm really interested to sort of follow the journey of like DNSSEC and see how it's being adopted. And if you want to learn more about it, I highly recommend checking Cloudflare out. They've written some really good blog posts on exactly what DNSSEC does. And that's it.